but yeah. So what is Inside Track, right? SAP Inside Track, it's a community organized event. It started, Darren? 2007? Yeah, I think, right? In London. Darren actually organized the very first Inside Track with Nigel James in London. It was a start of a grassroots initiative. And from there on, now all over the world during the year, there are like 25, 30 SAP Inside Tracks from Asia, South America, Australia, everywhere. We have a couple in Germany, and finally we arrived in Berlin. It was about time. The capital of Germany finally has an Inside Track. And it was only possible with the amazing help from SAP Labs, Bruno, Martin, to make this really work here. I'm just a community member. I participate in it, and I try to bring together a couple of friends. But really the most work for organizing that whole event was actually done by Bruno. So. And we should get started, but first of all, Martin wants to say also a couple of words. Martin is from SAP Labs, and we organized it like sort of cooperation between SAP IT and SAP Labs. Usually Inside Tracks are more community organized, right? I consider myself community. But actually, I'm just glad that we actually made it work, right? That it's finally in Berlin, this beautiful location, beautiful data space. I hope everything works out with the whole setup, what we have prepared, but for now it looks really good, so I think we are going to make it work. But I hand it over to Martin. You have your microphone.
Yes, I have my own microphone.
You see, that works already, that setup.
Thanks, Oliver. So first I have to correct you, so I was forced to say a few words. But I think it's okay. And to be honest, I didn't know anything about Inside Track before. Just learned from it, I think, 1 week ago or 2 weeks ago. And I'm very happy to see that SAP has a community, has a strong community, and I think that's very important. And I find it even better that we have this event here in Berlin, also in this beautiful data space, SAP data space, as you might know it or heard it before. And also thank you to the data space team for making this happening. And I don't know if you noticed that in Berlin, also from SAP side, there are a lot of things going on at the moment. So we have the SAP Berlin team established, and we're trying to engage much more with the ecosystem here, because we think in Berlin there is a rich ecosystem, there are a lot of events happening, and we are participating actively in those events like the Tech Open Air, as you might heard, or next week on the NKF Summit, also here in Berlin. So I think it's very nice to have you all here. I wish you a very nice day. So thanks, Oliver, for keeping the strings together and organizing it. And yeah, I wish you a nice day here. Enjoy.
And I have one or two last questions. No, not the last ones actually, but it's just starting. But so when we came together to think about how we make that Inside Track work, right, there was of course the idea. And the thing is, with Inside Tracks, when they happen in different locations, there's one in Hanover, in Hamburg, in Frankfurt. Usually there are no big SAP locations there. Here in Berlin, just 200 meters up the street, there's a big SAP office with 700 employees working there. So when we thought about doing this Inside Track, it was really getting to know people that not work at SAP and that might work with SAP software, because that is the community, right? It's not the SAP employees, it's the people that are using our software day to day at customers, doing implementations, consultings, or doing base administrator at some university running the SAP system. So I'm curious, who's here not working for SAP? Can I just see a couple of hands? Whoa. That's amazing, thank you, right? That's really, really cool, and that's what we wanted to achieve, definitely. And that most of the people here should be not from SAP, and we are really looking forward to get to know you, right? To get to know you better. And please make sure this will be a regular event. Usually they happen once a year, so don't expect it to be like every 3 months or so. It's once a year. We probably try to stay on that schedule with like end of August, early September. End of September, TechEd is coming up in Las Vegas, which is a big event, so it will be quite interesting maybe to see some stuff that is going to be presented at TechEd only, and we get some sneak peeks here. But then also I should mention the SAP Stammtisch. Yesterday we had a meetup at Mein Haus am See, And that is something that we we borrowed the idea from Frankfurt. There's an SAP Stammtisch in Frankfurt happening on a monthly basis, and I have been there a couple of times. I really like the idea, so maybe we can actually make that also work in Berlin and just have on a monthly basis bring people together, right? And it's Stammtisch, and if you don't speak German, it's like really drinking beer and talking about stuff that you might be interested in. Sometimes SAP, sometimes not. But the whole idea is you get some regular people together and have some fun on a monthly basis, right? So that's just honestly very amazing to see that so many people we don't know yet are here, and hopefully you're enjoying them very much.
Cool. Just some housekeeping here. We're gonna have probably in the next 10 minutes some Twitter feed here, so if you wanna give the speaker suggestions, inputs, or recommend something, you just use the hashtag SITSBER, then we're gonna have the live stream over there. We also have an evaluation board over there, so if you feel like leaving some comments to the organizers or for the speakers as well, we have some post-its and all sessions on that wall as well, so feel free to bring your inputs. And also I'd like to, of course, thank Grit, she's responsible for the videos, and Maria, that's over there. They're also, of course, an Oliver, like it was a teamwork, so thank you very much as well. And thank you for the speakers, right? So it's about your content, it's about you guys sharing some knowledge. So thank you very much. If you guys don't feel like being the photos or videos, just reach out to us, okay? Thank you very much.
And I think now.
Well, maybe can I get the screen? So about a year ago, I got back into machine learning after a really long break, and as part of that, I did this online course on Coursera by Andrew, and it's a really famous course for people doing machine learning. That course takes about 11 weeks to do. So it may go a bit quickly, try and keep up. Time for questions at the end. And even if there's not time for that, just grab me during the day, we can talk about any of it. But the idea here is to talk about what these various algorithms do rather than how exactly they're implemented. So the idea is that with that, if you've got a particular business use case, you'll know which one from the menu to pick, and then you can talk to a programmer or whoever about the actual implementation. So here's our menu for today. We're going to talk a little bit about what machine learning actually is, just as a quick recap. And then we're going to look at these 5 different kinds of machine learning algorithms. So prediction, where we're looking at what's going to happen next. Classification, recognizing images, that sort of stuff. Data compression, anomaly detection, so IoT use cases, servicing, that kind of thing. And finally, recommendation, so what to watch next on Netflix. So a couple of quick definitions about what is machine learning. The classic one is this one from 1959, when machine learning first got sexy, that it's about giving the computers the ability to learn without being explicitly programmed. So in other words, you're not writing a program to say do X, Y, and Z and then give me an output. You're generally using an overall algorithm and giving it a load of data and trying to train it in some way to do the right thing. So the more formal way of putting that is this from 1998, Tom Mitchell's definition, where we can say a program can learn from some experience E with respect to a task T and some performance measure P if its performance on T as measured by P improves with experience E, which is a really dry and boring definition. So let's try and look a bit more at what that actually means. So what we're looking at is we're trying to build models that do things. And these models have some parameters that change the behavior of how they do things. So let's say we want to try and measure the weight of a bag of fruit in grams. We might have a model that says the weight of this bag of fruit is A times x1 and B times x2. So there we're saying x1 is how many apples, x2 is how many oranges, and then A and B are the parameters of our model. So if we have a machine learning algorithm that's trying to optimize those parameters, it might come up with, for example, A is 85, B is 120. So then if we've got 3 apples and 2 oranges, we've got 85 times 3, 120 times 2, and that predicts our box of fruit to be weighing 495 grams. So that's the general form of what all of these algorithms are doing. We've got some model, the machine learning algorithm will give you the best set of parameters for that model to behave well on the task that you're trying to do. And that's pretty much what I just said. So yeah, as I said, we're looking at what these algorithms do. All the examples I'm going to show you, there's a lot of these 2D graphs with points and showing what the model's doing. The examples are in 2 or 1 dimensions to make it easy to visualize what's actually happening to tell you all about it. In reality, these models are going to have thousands or millions of inputs or dimensions, but that's really hard to visualize, so it's not very useful for teaching. But if you think that the examples I'm showing are really simplistic and not very useful, that's the reason, is because we're just using 1 or 2 dimensions to get the idea across. The actual business application would be using way more dimensions than that. And finally, right at the end, I'll give you links to the actual courses. So if you're interested in taking this further, you can do that yourself as well. So let's start then with prediction. So what we're trying to do with prediction is, given a set of input values, predict some output value. So for example, these are some business use cases. If you measure the acidity and carbon content of engine oil, it turns out it's possible to predict the amount of wear on your engine. Given the various parameters about a car, you can do a reasonable prediction of what it might be worth on the second-hand market. Quite a cool one when I do my online shopping every week for my groceries. Their system predicts what I should be buying each week based on what I bought in previous weeks, and whether I buy toilet roll once a month, whether I should have run out. So if I do my shopping, when I get to the end, it'll say, well, hang on, you probably will have run out of butter by now, you should be buying some. And then of course the classic one that everyone's talking about is automated driving, where you've got a bunch of inputs from car sensors, cameras, LiDAR, that sort of thing, and the output you're predicting is what's the steering and accelerator input we should be giving to the car so that we don't crash and get to where we're going. So the first algorithm we're going to look at here, it's a really simple one, and it's just statistics. And it's actually a really important lesson in machine learning. It starts at just statistics and gets gradually more and more complicated. And sometimes when you're looking at a machine learning problem, the simplest answer is just to use statistics and not get into deep neural networks and things like that. It's a lot faster to work with stats than it is to work with neural nets. So here, it's just one variable. We've got the house size in square meters, and what we're looking at is what the resulting house price is. And we've got a whole bunch of data points here. It's not a complete straight line, so here we've got 2 places that are roughly 200 square meters, differing from 600 to 800,000. But that's the overall real-world data that we're trying to model. So if you do linear regression on that, that will fit a line to the data. So this is something, linear regression is in Excel. That's how simple it is. It's technically machine learning, but it's statistics. And this is actually an Excel graph where I just said, do me a linear regression on that data. And what that will do is find the best fit line. That line has 2 parameters, the slope and the offset, A and B. So it's a simple 2-parameter model to fit a line to some data. Now, the line isn't always straight. It may be a curve. So in this case, the data fits a quadratic curve better. And we're saying, OK, so it's quadratic. It's A, B, C for A times size squared, B times size, and C. It's a 3-parameter model. That means we can fit a curve quite nicely. And this also gives you one of the other lessons in machine learning is, as well as the actual parameters for the model itself, you've got to choose the right model. A lot of the art of machine learning is in choosing the right model for your problem before you actually let the machine learning algorithm optimize the parameters for it. So often you're just looking at and exploring your data and seeing what general shape it is before you set the algorithm loose. So now we come on to neural networks, which is another way of doing prediction. So with a neural network, what we have is our inputs here. So this could be our apples, oranges, whatever, or our car engine size, age, and mileage. We have these hidden nodes here, and that all feeds through to our actual predicted output. Now, how a neural network works is the values here are all multiplied by the weights on these lines here. So each of these lines is a parameter in our model, and we multiply this value by the line to come in here, and then each node sums up everything that's coming in, puts it through a simple function, and then that's the output. So it's relatively simple. We're just doing multiplying and adding, putting it through a simple function, usually a sigmoid or some kind of curve. But what you can see is for a fairly simple model with 3 inputs and 1 output, we've gone from not 2, not 3, but we've gone to 31 parameters. What that tells us is that neural networks can be a lot more powerful, but trying to optimize 31 parameters takes a lot longer than trying to optimize 2 or 3 parameters. Now, where is that useful? That's typically where we don't really have a good model, we can't really describe the shape. So this data here is applicable to everyone in the room, I think. This is the price of a Maserati car, according to age. So if you get a Maserati that's nearly new, it's a logarithmic scale here, it's of the order of 100 to 200,000. As that car gets older, it exponentially gets cheaper because no one wants a 5-year-old Maserati. People who buy Maseratis want a new Maserati. So down to about 30 years old, these cars just get cheaper and cheaper and cheaper. And if you want a really cheap Maserati, buy one from mid-80s, you can get a Maserati for about 10,000. The servicing costs that per year, but you can get that. But here's where it gets interesting, is suddenly, once it gets to about 40, 50, 60 years old, it's a classic car. Now it's worth, up to $1 million if it's 60 years old. And there's no obvious curve that fits that. There's no quadratic, there's no good model. So that's a really good example of where you'd give it a neural network that and just say, look, here's the data, figure it out, do me a model. So I'm going to talk a little bit more about where neural networks came from in history, because it's, obviously they're really sexy now, and it helps a little bit to know when they've been sexy in the past. So back in the 1950s, that's when neural networks really started. It's the really early days of computers. Turing had written his papers on artificial intelligence, and they really thought back then that they could produce an intelligent machine. They called this really great 50s science fiction name the perceptron. And that was actually a physical neural network with resistors and things, and they built it, they trained it with resistors with dials, and there's robots changing the dials for the weights. And they got some interesting results. It could detect certain patterns and worked quite well. But then in the 1960s, someone did a theoretical analysis of that and proved that there were really simple problems like the binary XOR problem. So saying, are 2 inputs just the same or different, that couldn't be done. And they thought, well, if it can't even do this simple binary problem, these things aren't really very useful. So they just went out of fashion completely. Then back in the 80s and 90s, which is when I first started looking at them, they realized that if you had a multiple layer network, it didn't have this theoretical problem. And that with multi-layer networks, you could actually do something reasonably useful. And we had the computers then were powerful enough to simulate these things in multiple layers. So back then we started doing some toy problems. We could recognize some handwritten digits. But what happened is that beyond these lab demonstration problems, the computer hardware back then just wasn't powerful enough to train on real-world business problems. And so they went out of fashion again, and we really went through the 2000s and most of the 2010s using just pure statistical methods again. And then in the last few years, you've seen this big explosion again, where it turns out if you have an enormous amount of computing power, like if you're Google or Facebook and have a big data center full of GPUs, and you throw an enormous amount of data at it and make a few small tweaks to how you do the training, then you can actually get some interesting results. And that's what we've been seeing in the recent years. And when we talk about the increase in computer power, so if we look at the last 50 years, we take two jumps. So from 1967 to 92, that's 25 years. And from 92 to 2017 is 25 years. So in this 25 years here, a supercomputer back in 67 did 2.5 million operations a second and cost $60 million. 25 years later, the Cray supercomputer, it had 5,000 times the speed up, so that's 13 billion, not million, so 13 billion operations a second, and a quarter of the cost. So in 25 years, we've got 5,000 times faster, 25% of the cost. Now this is where Moore's law breaks. The next 25 years, it's not the same scaling again. From 92 to now, we've made a leap. It's now 70,000 times faster than then. So not from 1960s, but from the 1992, we've got this 70,000 times speed up. The cost of this machine that's 70,000 times faster is $150,000. It's 1% of the cost of this machine from the 1990s. Specifically, this supercomputer from the 1990s that cost £15 million, if you benchmark that, it's got almost exactly the same results as a modern Samsung S8. It's just crazy the amount of computer power that we've got now. And that's really a large part of why neural networks are now popular. We've had this enormous explosion in computer power that finally makes it feasible to do interesting problems. So, with that out of the way, let's move on to our next set of algorithms. Classification. Basically, is this a picture of a cat or is it a picture of an avocado on the internet? In terms of business problems that we might be interested in, so if we've got an image of a skin tumour, is that a benign or a malignant tumour? We can classify it into one or the other. Really useful in business, if we've got an image of a handwritten digit or some handwriting, what actual digit is that? From the image, what's the actual word, what's the actual digit? Really good SAP example that's out at the moment. If we've got a video image from a football match, find all of the logos in it and which logos are in that image. And also from an SAP example, if we look at the text in a customer service ticket, can we classify that and send it to the right team? So how do we do that? We looked at linear regression in the first slide. Very closely related, also available in Excel, is this logistic regression. So the difference is linear regression is giving you a continuous value as an output. Logistic regression is giving you basically a yes-no example. So here we've got no and yes. We've got tumour size in square millimetres, and here's our observed data that these smaller tumours tended to be benign and the bigger tumours tended to be malignant. And what we're looking for is where's the threshold that makes sense to do that classification. So if we run logistic regression on that data, it will basically give us this line here. And as you can see, it's not perfect. Just like in the linear regression case, it wasn't exactly modelling the data, but it was giving us the best fit. And it's the same thing here. We can see the vast majority of these things are classified correctly. This one isn't. And similarly up here, that one isn't. And that's another important thing to realise, is that with any of these algorithms, it's going to give you a good answer. Very rarely will it give you a perfect answer. And one of the interesting things that you can look at, I won't talk about today, is actually how do you decide that? What are the ways of deciding how good the answer is? It doesn't have to be just a simple straight line either. So if we go into 2 dimensions now, so here again we're going into multi-parameter models. So here we've got a bunch of points and we're saying these are, these might be cats, these might be dogs for some measure of height and weight or something like that. So we're saying with logistic regression, it will give us A, B and C to define a line in 2 dimensions. AX plus BY is greater than C. That gives us this line here that will classify things. And once again, it doesn't have to be a straight line. If we decide that actually everything within this circle is of one type, everything outside the circle is another, then you might remember this from high school. That's the equation for a circle or an ellipse. And here we've got A, B, C, D, E, F. We've got 6 parameters. to decide if something's inside or outside of a circle. So again, quite easy, but compared to what we were looking at with linear regression, again, we're getting into a few more parameters, a little bit more difficult to solve. To be honest, this is only difficult to solve if you're doing it on paper. If you're throwing this at Excel, it's going to be absolutely instant. So as well as regression, again, we can use neural networks for classification as well. So in this case, the output value is either close to 0 or close to 1. And this is an actual example of classifying irises, the flowers. And if you measure the sepal length and width, so the sepal is the green leaf bit under the petals, and you measure the petal length and the width, and you train that on a whole bunch of examples of these 3 particular types of iris, then you can actually get a good neural network model that will classify irises according to their type. And as we saw before with our 31 parameter model, in this case we're just classifying into one of 3 types with 4 inputs, and we're already up to 51 parameters. So again, we're seeing with neural networks, to do anything useful, you're getting to at least 10 times the complexity, even for relatively simple models. In the real world of deep learning, these are actual models used by Google, and this is one of the best performing in the world at the moment, ResNet 50. It can do about 99% accuracy on classifying images. It's got 23.5 million connections in its network. So given that to train a neural network, you have to evaluate all 23.5 million, apply some changes to them for the next set of data, and you have to repeat that cycle typically millions of times, you start to see where supercomputer data centers are required to actually make this work. So then we go on to the third of these algorithms. This is support vector machines. And Tal likes these. He's got the t-shirt. You'll see that shortly. It works in some ways quite similar to logistic regression, just using a different algorithm. So where logistic regression was kind of finding the best line where things fell one side or the other, with support vector machines, it's looking for the best margin. So see the thickness of this line. It's looking to create the line that you can make the thickest that still completely separates these values. And that tends to behave better in real-world problems. In fact, before neural networks got sexy again throughout the 2000s and the 2010s, this was the state-of-the-art way of recognizing things, and still is for many problems. So when would you use logistic regression or support vector machines or neural networks? So I'm not going to go through all of that boring text, but generally speaking, logistic regression is going to work well for small models. For models where you've got roughly of the order of thousands of inputs, then support vector machines work really well. And for models where you've got lots more inputs, millions, then neural networks work really well, in a nutshell. So finally, in terms of classification, we're going to come to a different kind of algorithm altogether. So far what we've been looking at is so-called supervised training. So in other words, you know the output for any given input in your training data set at least. So you can say, if you're not close enough, then tweak it, make it better next time. You know what you're looking for and you can give it feedback. Clustering, k-means clustering, you don't need to label the data at all. All you need to do is to say, look, I think my data might be clustered. I think there are going to be k number of clusters. So here's all of the data. Just partition it yourself according to what you see in the data. And that's what the algorithm does. And the only thing we actually need to choose is this k, this number of clusters. So this works really well in business for the apparel industry. So let's say we want to make a bunch of t-shirts for our customers. And it might be that we just want to make them in 3 sizes, small, medium, and large. So in that case, then we'd give k equals to 3 to our algorithm. And in this case, a simple 2-dimensional input, so we get the height and weight of a sample set of customers. And as you can see here, the algorithm has formed these 3 clusters. And that will then tell us, if we design our small size shirt to be based on this height and weight, our medium to be based on this height and weight, and our large to be on this height and weight, that will give us the best fit to our known customer base. Similarly, if we want to be a bit more customized, we can say, well, we're actually going to do 5 different, we set k equal to 5, we can do xs, s, m, l, xl, exactly the same data, it will find 5 clusters instead. And so the art in k-means clustering is, the good news is the algorithm really does all the hard work for you. The hard bit is picking the right number of k. So particularly, imagine producing the t-shirt sizes in business. You're looking for a sweet spot where you've got enough different sizes that everyone's happy with the size that fits them. But at the extreme end of this, you don't want to be producing a bespoke t-shirt for every single customer. So it's finding the value of k that makes sense for your business case. So that's classification. Now we're going to look at data compression algorithms. This is fairly simple stuff. So essentially, in data compression, there's 2 things. One use of it might be, if we've actually got 1 million inputs for our neural network, that might be too much even for our supercomputer data center. So can we do some sort of data compression on those inputs so that instead of having 1 million inputs, we've only got 10,000 inputs, and then that will work on the size of hardware we've got. We might lose a bit of information, but hopefully we keep the essentials and we get to run our neural network in a feasible amount of time. And the other one is the more classic case of, let's say we've got an image that's got a whole number of pixels. Can we store that in a fewer number of bytes than we have pixels? So just classic data compression, like JPEG. So the first way of doing that, this is principal components analysis. This is a pure statistical technique again, and it can work across any number of dimensions. And what it does is, let's say in 2 dimensions, here's our data. And it looks like linear regression. It's not. It's a slightly different thing. We're not predicting A from B. This is actually just a 2D data set, a bit like we looked at on the clustering example. And we can see that our data lies mostly along this line here. So what principal components analysis allows us to do is choose the number of dimensions we want to map our data to. So if we say we want to go from 2 dimensions to 1 dimension, PCA will squash everything down to the best line possible. So it will choose the line and it will map everything down onto that one line. So now effectively we can ignore these 2 dimensions. We can see these as just values along one single dimension. So we've collapsed 2 into 1. We've lost a little bit of data here, but the idea is the PCA algorithm has chosen the best line here that we're minimizing what we lose. So yeah, that's used typically to speed up neural network training, as I said. Also for the k-means clustering we looked at earlier, if we've got a bunch of input dimensions and it's taking k-means clustering too long to run, we can use PCA to reduce it to the essentials and find our clusters in fewer dimensions, and it will run more quickly. The only thing you need to know about k-means, principal components analysis, is that you need to do a bit of pre-processing on your data to make sure that all of the numerical values are in approximately the same range. So you see here we're looking at house size in square meters and price in thousands of euros. The important thing is we're using thousands of euros, so these things are both in the region of hundreds, so that they then work with PCA. If this was actually in the thousands, then we'd just have this really steep line and it wouldn't behave as well. So it's simple to do. You pretty much can just look at the mean of your data and scale it accordingly. So the second way of doing data compression is using a neural network again, of course. So it turns out that if you train a neural network to produce exactly the same output as the input, but the structure of your neural network has fewer nodes here than you have here and here, then if you say present a bit of an image here, it will produce roughly the same image out here, and you can extract the data here and store it, and that's your compressed data. And then to reconstruct the image, you can just feed the data back into the hidden layer and reproduce the output again. And it turns out that actually this mathematically behaves quite similarly to principal components analysis, where these are the dimensions in your principal components analysis. So there's not much more to say about data compression. It's a fairly simple case, and without going into how it's done, it would get very complicated. So now we get into our next class of algorithms, anomaly detection. So this is quite useful for, in business, fraud detection is a really good one. If someone has an unusual spending pattern, we can predict the failure of engines and turbines. You know, if the vibration starts to get a bit much, things get out of a certain band, that's good. Server monitoring is a great one. We can predict that hard drive's about to fail if it's anomalous. Intrusion detection in networks, we can find hacking attempts. And even car breakdown prevention. In England, the AA, which is the equivalent of ADAC, they have an app now that when you're driving with this app, you plug it into the diagnostics port on your car. Instead of having to call out when you break down, the app will tell you if you might be about to break down soon, and then you know to go to a garage. And of course that saves the rescue services a ton of money through not actually having to come and see you, and saves you a ton of hassle from actually breaking down. This thing can say that, you know, you're likely to break down in the next 2 days. So how might we do anomaly detection? Well, you can think of a number of ways of doing it based on what we've already talked about. So if we've got a labeled data set, we might be able to use classification to say, is this an anomaly or not? Well, the problem is, though, anomalies tend to be anomalous. There's no real pattern. It's hard to come up with labeled data because anomalies are by definition rare and unusual. Maybe we can use k-means clustering to say that this cluster is normal behavior and this cluster is abnormal behavior. Again, the problem there is normal behavior tends to cluster well, but anomalies are, you know, anything can happen, so they tend not to form a cluster. They're just random spots of data in the rest of the data space. Or we could use a prediction algorithm, and this is where there's some research happening. If you're actually using time series data, if you predict the next value in a time series and the actual value that comes along is a lot different to your prediction, you can say that that's an anomaly and maybe we should do something about it. But more classically, how anomaly detection is actually done is it essentially assumes that everything, all of your data fits a Gaussian normal curve, or it can be made to fit a Gaussian curve if you do some mathematical tweaking on it. So, you know, here's our actual set of data points. That might be temperature and vibration on an engine. And you can see they're a bit more clustered tightly here. And they follow this classic bell-shaped distribution. So if we can get our data to fit that Gaussian model, then what happens is we can say that anything within 2 standard deviations, for example, we define as okay, and anything outside of 2 standard deviations is an anomaly. And then mathematically, you can see here, you can set that number of standard deviations. If you say 1 standard deviation, about 70% of all your data would normally fit within 1 standard deviation, 95% would fit within 2 standard deviations, and 99.7% would fit within 3 standard deviations. So you can tune that and say, you know, how unlikely an anomaly are we looking for, and then if it occurs outside of that, we know to raise the flag. And another way of doing anomaly detection, this is a slide I've stolen from another SAP presentation, is if we look at principal components analysis, as we did before, if we use that first, then we can use that to find the best dimensions to look at, and then we can just apply the Gaussian thing on the axes found by principal components analysis. So we can use that to fine-tune and get better results from a given data set. So that's anomaly detection. So finally, we move on to recommendation. So this is the classic Netflix or Amazon, what do I watch next? What do I buy next? What Coursera course should I do next? Back to my grocery example, you know, if I've bought this kind of butter, maybe I'd like to buy that kind of cheese. Or in the SAP Hybris, they do customized special offers. So if you're shopping around on a site, the system will actually design a special offer that works just for you. So an example of that is movie ratings. So let's say we've got these movies here: Love at Last, Romance Forever, Cute Puppies of Love, Non-Stop Car Chases, and Swords versus Karate. And we've got 4 people: Alice, Bob, Carol, and Dave. Now it turns out that Alice has rated some of these movies, but not Cute Puppies of Love. And similarly, Bob has rated some, but not Romance Forever. So if we see that, you know, Alice and Bob both like Love at Last, both of them are not really keen on car chases and karate. So if we see that Alice has rated Romance Forever as a number 5, we can probably guess that Bob would also rate that as a number 5. And similarly, if Bob's rated 4 for Cute Puppies of Love, we can make a reasonable guess that Alice would also like Cute Puppies of Love. So that's the basic sort of, when you see Netflix ratings about what it thinks you would like, that's what it's doing. And as a refinement of that, we have the collaborative filtering. This is closer to how Amazon does it as well, and now Netflix. If you take these predictions, you can do some further filtering and actually start to figure out genres. So we figure out that people who like these two movies tend to like these two, and it's almost like a clustering. And then we start to be able to say, well, that's something we can call romance movies. Similarly, we can have something we call action movies, which again is another kind of cluster. And it turns out it's not using k-means clustering, it's using some other maths under the skin. You can actually define as many of these as you like. You don't even have to label them. And essentially, it will just figure out as many genres as you like. So if you actually go into Netflix now, you'll see it's actually starting to create these customized genres that are really specific to you. It's sort of, in my case, it will say, subtitled anime movies about robots. Here's the selection that you like to look at. It's creating custom categories for me, and that's how this stuff works. So that's kind of all of the algorithms I wanted to talk about today. That there are more. These are the ones that I covered in the particular Coursera course that I did. The reason I haven't gone into the detail of them is, here's how you do collaborative filtering. It will probably take me about 30 minutes just to describe each slide of how that works. So instead, if you're interested in taking this further, there's an open SAP course. It just takes 2 or 3 hours. That covers a really high-level business case, so probably not even as technical as I've done here. But it gives you some good oversight into what machine learning is about and how you can use it in business. Everything we spoke about here is available in this 2011 Coursera course, which you can do for free. If you want an official certificate at the end, you have to pay a bit of money, but the course itself is free. I highly recommend that. It's taught by a really great guy, Andrew Ng. And just in the last few weeks, he's released a new specialization that follows on from this course. You do have to pay more for that, but you can trial it for free for 7 days. And that gives you all of the stuff that happened since 2011, which is basically all of the new sexy stuff, all of the deep learning, TensorFlow, all of that cool stuff. And if you pay them for that, then you actually get access to GPU instances to run it on as well. So that's where to go next from here if you're interested in getting involved in machine learning. So with that, thank you very much. And I think we've got about 5 minutes for questions, if anyone has anything. No? 7. Cool. So, any questions?
So, what have you done with all this, other than presenting?
Mostly learning so far. So the image compression example that I showed, that was the topic of my PhD. So I've done that. What I'm doing right now, I'm on the machine learning platform team at SAP. For the last few years I've been working on cloud architectures. So what I'm doing right now is actually designing the training platform for SAP's machine learning. So actually putting the GPU systems together and the training software. So I'm not doing the actual machine learning at the moment. I'm doing the engine on which our data scientists can do the machine learning.
How do we use this knowledge in SAP? So, okay, we understand it, we do the courses, we understand it's possible, but how do I use it in a SAP landscape? So in SAP, mostly it's standard software,
Mm-hmm.
and down the line it will be on S4HANA, all the standard software, and the custom development will be on the SAP Cloud Platform. So there, how do I use this? For example, if I have a client and they have a custom business process where I can use all this neural network and machine learning,
Yeah.
how do I implement it using SAP software?
So yeah, the question is, how do we implement this using SAP software? And there's a couple of answers to that. So the more statistical techniques that I looked at, the regression and things like that. So with a HANA system, you get R, the statistical package. So R would support all of those statistical methods. For the neural network stuff, at the moment, the SAP offerings are at the API level. So if you wanted to do the SAP brand recognition to getting logos in video, you just use that as a service. What we are moving towards is an idea of what we call bring your own model. So it may be that, let's say we have a product image recognition. We may have a pre-trained model that works generally quite well for most images. And then as a customer, you may say, well, here's all of my product images. And then you'd run that on our training system, and that would retrain that neural network to be really specific for your case. So it's really at the level that I've spoken about here, about knowing what the algorithms can do. You don't really, as an SAP customer, you don't really have to know anything about how they work. You just have to know that the bring your own model stuff is more of the neural net kind of things, and that in general, in any of the regression techniques and I think support vector machines, you could probably do within R on HANA. And then at some point, we may look at also connecting the machine learning platform into HANA itself to be able to have a more direct low-level access. But that's just kind of thought experiment at the moment.
Okay, one follow-up question: that what features are already available in the SAP landscape?
So the question is, what are the currently available features? What are the status quo? I'm not in marketing, so I think the best answer I can give to that is to wait for a couple of weeks and see what's announced at TechEd. Okay.
You had a really nice example with t-shirt sizing by machine learning. What do you think, what is the reason for e-commerce retailers that they still struggling to find the right size for their customers? Could it be that the parameters are not the good ones that they choose, or?
Really simple. They're not using machine learning. and that's actually, it's a really important point. The stuff I've talked about here, no one's really talking about machine learning at this level. This is not stuff that businesses are being taught about. It's really new. And that's one of the reasons I wanted to talk about it here, is to actually try and get it out to customers and to businesses. So this is what being an intelligent business is about. And really only the massive Google, Amazon, Facebook people and a few others are doing that. Very few are doing it, but anyone can. Any more? Yeah.
Hi. First of all, thank you for the nice talk and kickoff. I just want to ask you, as a novice statistician, how do you reconcile the sort of brute kind of approach that deep learning has usually, of like millions of parameters and so on, with what we usually get as a recommendation of a parsimonious model? And is it always the case that we get like billions of parameters, or do you also have an example of like a typical 2-3 parameter model that's working fine?
Yeah, I think where it's just, so the question is, if I can interpret it slightly, it's, so there are, when do we use statistics and when do we just have a massive neural network and throw data at it? I think the best time to use statistics is when you have a statistician. There's a massive grey area in between where you have data scientists, and then there's an area where you have people who just aren't thinking about it and just throw a ton of data at a neural network. And throwing a ton of data at a neural network is definitely not always the best way. And in fact, I think that the best way to start any machine learning project is probably to start with the statistical models. Start with the simplest possible statistical model and see if it works. And it could be that a simple linear regression or logistic regression will actually give you the performance you need. But far too many people think, yeah, this is machine learning, we have to have a big neural network. And then they're going to waste 6 months or a year trying to tune it and spend a ton on Amazon Web Services on GPUs when they could have done it in 5 minutes in Excel. Okay, so I think we're about out of time there. So again, thank you very much for your attention. I hope you learned something, and yeah, feel free to talk to me later if you want to learn more.
Nice way to kick off SAP and Soundtrack. Good. Give it, Tal, take it away.
Thank you. So hi everyone, I'm Tal, and I'll be speaking to you about understanding your clients.
Please use the microphone.
Oh really? I have one.
Yeah, we have two.
Ah. Alright, so I'll be speaking about understanding your clients with deep learning, and I guess we'll explain all of those things. I promised the organizer I would say Don't forget to tweet about the talk, tag me, and tag Sitbar and SAP Berlin, and spread us on social media. All right, let's get started. So I guess let's start with the punchline, right? And no presentation is complete without Dilbert. So here's the boss saying, hey, we have a gigantic database full of customer behavior information. And Dilbert's like, excellent, we can use nonlinear math and data mining technology to optimize our retail channels. And that's pretty much deep learning, right? We use nonlinear math and data mining to optimize stuff. That's exactly what we want to do. And then oftentimes I feel as a data scientist and as a consultant that when I talk with my business stakeholders or clients, usually I get something like this. So if that's the same thing as spam, we're having a good meeting here, right? So sometimes the business, as Aaron mentioned, kind of misses the business value or what we can really do with these things. And I hope in this talk to kind of show a bit about, maybe we'll talk about the algorithms, but also the potential for how we can interact with our end users within our own organization and kind of expose data that we have but we can't really use at the moment. All right, so I guess at a slightly lower level, what we'll cover today is we're going to talk about text. So when I say understanding our clients, so I'm a text guy. I work with NLP and mostly with chats. And if you think about it, we interact with customers and with other people on email, on chat, on SMS, over the phone. We have transcriptions. And there's a lot of information there, right? So we express the things that we're interested in or our opinion about them. And that's very valuable to know. And then on the other side is we don't just have our customers saying this stuff, we say it, right? So if you have a sales organization, you're holding a CRM, you have good sales reps at least, they're summarizing their calls and you have information there. What did the customer say to the sales rep? What did the sales rep think about this lead? We want to access that. Or support tickets, right? So that, I think Darren mentioned that. Sometimes you want to automate your support flow. And you have these tickets that are open, there's text in there. And if you could automate that process based on the content, you'd save a lot of money, you'd optimize it, give better user experience. So these are all things that when I say we want to understand, that's what I mean, right? So we really understand the context in text and take actions that help us. More specifically, what we'll cover today, or the way the rest of this talk will look like, is I'll tell you a bit about why this is important in general. And then I think I'll break into two parts. So one will be about understanding, and the other will be about deep learning, right? So we'll talk a bit about where we are today and what we can and can't do in general in terms of understanding. And then I want to go into the part of deep learning. So deep learning is a wide field in and of itself that has really enabled us to do cool things with text. And then we'll connect them and talk about understanding with deep learning and show some practical examples. Great. All right. So who am I, if I didn't say so before, right? Why are you listening to me? I don't work for SAP. I've barely engaged with SAP, I'm ashamed to say. Today, I'm a data scientist consultant at Citibank. I work with chats. For those of you who are more into text, right, or if you ever consider what a chat or a WhatsApp message look like, it's really horrible language in the sense that we don't obey rules, we have slang, we have spelling mistakes, we use emojis, right? It's not like you can't read a grammar book, infer the rules of English or German or whatever, and then expect your algorithm to work on chat data, because we don't talk like that. That's just wrong. And one of the ways we handle that is working, instead of assuming that like the atomic unit of text is a word, we work character by character, byte by byte. So that's become kind of my day job and my hobby, and I'm very into it. I like to build stuff. So this tree is, I built this with a friend. It's a 4-meter tall tree built out of old Coke bottles full of LED lights that we programmed with an Arduino and put in the middle of the desert. So I always like to show it because I'm proud of it. And moving on. All right. So I promised you I'd say, why is this important? Why should you care? So who here reads XKCD? Very bad. You all should. All right, that's better. Thank you. So XKCD is the ultimate geek comic, right? This guy, Randall Monroe, I think his name is. And he's very, very smart, and he puts out like a comic weekly. And he's got this one, which is a classic that he put out in 2013. And he's got, the annoying manager comes to the developer, and he's like, when a user takes a photo, the app should check whether they're in a national park. And the developer's like, sure, simple, easy GIS lookup, right? So every photo has kind of geographical information in it, so you can just look it up and see it's at a national park. And then the manager's like, yeah, and along the way, check whether the photo is of a bird. And then the developer's like, hey, I'll need a research team and 5 years. And the punchline is, hey, in computer science, sometimes it's hard to explain the difference between the easy and the virtually impossible. And what I want you to notice is this came out in 2013, and the guy wrote is like, wow, recognizing a bird in a picture is virtually impossible. Okay, that was the state of the art 4 years ago. But last year, what we were able to do is this, right? So we can take pictures of a bird, and not only can we recognize there's a bird in there, but the algorithm will actually label the picture for us in proper English, right? 2 birds sitting on top of a tree branch. So think about the complexity of understanding of the image. It recognized the bird, it recognized the tree branch, it understood that the bird is sitting on the tree branch. It can count 1, 2, even though it counts wrong. There's a 3rd bird there. And then it can take all of that information and generate a sentence. So 3 years ago, recognizing a bird was impossible. And last year, we can do this and it's like easy. You know, you can download it on GitHub and it works. So I think that when things go from being absolutely impossible to absolutely trivial in 3 years, we should pay attention because there's a lot we can probably do with this. Yes, moving on. So let's talk a bit about what we can't do. And this handsome gentleman over here is Peter Norvig. I think he's touched all of our lives in the sense that he was head of search at Google and he's at some senior research position there. And many years ago, before I was born in '76, he wrote a PhD. And the title of the PhD was called The Unified Theory of Inference for Text Understanding. And I bring this up because, first of all, it's really cool to bring old stuff, right? It's like hipstery. But second, he made a very interesting observation in his PhD. He says, what do I want? So let me just read this. This is the first page of his thesis. And he says, people are very good at interpreting text and making inferences. They generally do not notice when the text is underspecified, and they have to make inferences to resolve ambiguities or to gain a fuller understanding of the text, right? So, said more easily, hey, I can tell you something, and even if I leave out details, it's really easy for you to kind of complete them, right? Like, hey, I'm in Berlin, right? Everyone understands I'm in Berlin, Germany, and not Berlin, Massachusetts, right? That's easy for you. But for the computer, not so much. So he brings this really awesome example and says 4 things we want to be able to do with it, right? And this is just a short paragraph from a fairy tale, and the whole PhD is about this paragraph, right? It's mind-blowing. So he's like, the story goes, in a poor fishing village built on an island not far from the coast of China, a young boy named Chang Li lived with his widowed mother. Every day, little Chang bravely set off with his net, hoping to catch a few fish from the sea, which they could sell and have a little money to buy bread. And, okay, so that's the paragraph. Does that make sense, right? There's a boy, he lives on an island, there's a sea, he's brave, he goes with a net and, catch fish to sell, right? So they have money for bread. Wonderful. Now, as readers of the text, here are a few things that are kind of obvious to us, right? There is a sea, okay, because that's in the text, and it is used by the villagers for fishing. And the sea surrounds the island, and it's part of the coast of China, right? So that was obvious. Anyone not pick up on that? Excellent. Okay, Chang intends to trap fish in his net, which is a fishing net, right? So obviously that's a fishing. Did anyone hear this story and think that was a butterfly net? No, but if you think about a computer, it doesn't have the information to infer that. And then so those are 2 tasks that are very, very difficult and we can't do. And then 2 tasks that today we can do very, very well. The word which, in which they could sell. So where is it? Catch a few fish from the sea, which they could sell. So the word which refers to the fish and not to the sea, because grammatically you could parse the sentence and understand that the thing that they're going to sell is the sea. So we want to be able to tell the difference between that. So today we can. We're quite good at that. And the final one, the same concept, is the word day. Okay, so point being from this slide is there are some things that are today we're quite good at, such as resolving what does day refer to, and some things that we're completely lost at and we have it's just like hopeless or very frustrating, at least as a practitioner, right? Which is understanding kind of context and making inferences that for a human are trivial, but for a computer are still impossible. So yeah, things are very bad in that sense. But we can do a bunch of really cool stuff, okay? So here's a list of things that we do really well today. So translation, if any of you use Google Translate, you may have noticed in the last year that the results really, really jumped. Google published a few papers and about what they've done. They say that in the last year of work using neural networks for translation, they've made more improvements than they made in the last 10 years. And you can see examples online of the difference in quality of the translation, and it's quite astonishing. Even to give a little anecdote there, they trained a toy system, or kind of a crazy example system, where they taught it to do translations from English to Korean and from Korean to Japanese. And then without showing it any examples, they got the system to do English to Japanese direct, right? So it would do an intermediate representation by itself and go without having to train it on that particular translation. So that's pretty cool. Other things we want to do, entity recognition. So this is my like professional bread and butter, right? The user, I don't know, if he talks in a text and you want to understand he's talking about this product and he's talking about this person, right? Maybe we want to know when we're mentioned on Twitter by name and not by handle. So we need an algorithm that can recognize that. That's entity recognition. Sentiment analysis. Does the customer like this? Is the support he's getting happy? Does he hate this product? Does he think this particular attribute is wonderful and we should amplify it in our marketing? Imputation. So this is, I guess, not a very common task in industry, but sometimes you have missing data, right? Maybe you did a transcription of a sales call and the transcription isn't perfect and you need to fill in missing words. So how do you do that, right? And we can, and it works quite well. Dependency parsing is boring, so I won't talk about it. But maybe what's important is this is hard. And the reason it's hard, as I said before, is because the rules of language are ambiguous. So even if you have a good understanding of grammar, you're a trained linguist, still the rules are difficult. There are a lot of subtle points and outlier cases, etc. But that doesn't even matter because people don't follow them, right? So I think I have decent English and I've probably made 100 grammatical mistakes since I started speaking. Subtle things in pronunciation and grammar. And we all do that, especially when we write informally. We don't obey the rules. So we can't build a system that follows the rules and expect it to work, right? And finally, and this is a fact of life that's very unfortunate as a data scientist, but all data is dirty, right? So data gets stored, the engineer that's storing it does a crappy job of it, we don't define it well, right? There's noise in the signal for whatever reason, and in the end, the data's junk or semi-junk, and that's a fact of life, and we have to deal with that, right? So you can't say the data is junk and we won't have product. The data is junk and we need to deliver. But we need to be able to, I guess, prepare ourselves spiritually for the frustration, and then also have algorithms that can actually handle that or work with it. Yeah, questions thus far? Excellent. So let's move on to the deep learning part. Okay, so that's kind of our background and understanding. And to kick it off, I want to kind of compare, I would call it old school machine learning and deep learning. And I think if you consider what goes on when you do machine learning, so these algorithms that we were talking about before, you need to push in features into that. You need to have the machine look at this, this, and this, right? So the housing price, the housing size, and from that predict something. And if you think about tasks that aren't numerical inherently, so maybe recognizing a logo or recognizing a face, recognizing an engine in a picture, these are good examples. What are you putting in the algorithm, right? It just takes in numbers. So what are you putting in there? And one of the things that we traditionally did in computer vision was this nice guy. This is called the Sobel operator. And this star means convolution for anyone who remembers one-dimensional convolutions from calculus. So this is the expansion. If you like computer science, it's equivalent to some manipulation of the Fourier transform. Very boring. And what the Sobel operator does is it takes a picture and it finds the lines. So it kind of highlights where the edges are of an object. And from that we can come, all right, there's something here, right? We just get the borders. So that's great, because now we have a feature that's a bit more usable for object recognition. But it's still not very clear what we're going to do with this thing, right? Once we went from here to here, on the one hand, we have a better representation, and we still need to do a lot of work to keep doing it. Now, the other thing is that Sobel, for which the Sobel operator is named, was very smart, and he figured out the Sobel operator. But, and this is an unfortunate fact of life, most of us are dumb, and we're not going to figure out the Sobel operator. And so we won't get these wonderful features. So here's what deep learning does for us, right? It's like, you don't need to be smart like Sobel, I'll do it for you. And basically deep learning is you stick in raw data, or very close to raw data, and you have all your millions and hundreds of billions of parameters, and what the network does fundamentally is learn various layers of representations of your data, right? And those representations are exactly the relevant features. So if you think about Facebook, right? We all have Facebook, and it recognizes our faces in pictures and says, tag this person, right? How does it do that? How does it know who I am? So that's exactly with deep learning. And what goes on is you feed it the picture, and it has this neural network, and the lowest layers learn these really basic features. So these kind of lines, right? Little curves, maybe differences in color, but things that are very, very local. The next layer will look at collections of these, right? And learn something a bit more sophisticated. So maybe an eye or an ear, right? These basic shapes. And you keep stacking those up, and eventually you end up with something that can recognize a face, right? So say person or not person, and eventually can recognize Tal and be really creepy. But the beauty is that you don't have to hand engineer features, right? You don't have to tell it, all right, if you see this particular shape, it's a nose, and if you see this particular shape, it's an eye. And you know, if you have someone who's missing an eye, what does your algorithm do? The network handles it for you, and then you don't have to do this, and that's really great. Yes, good. All right, so that's all nice and good, but so far, like the problems we've talked about are either numerical or image. But I promised you I would talk about text. So what is deep learning given us for text? And I would say two fundamental things, all right? So one is the ability to handle inputs of arbitrary size. So if you think about it, right, we'll have a collection of chats or documents or whatever, and some of them will be really short, like that's great, and some of them will be very, very long, like hi, I'm a customer based in Berlin, and I ordered your product, and I was very frustrated because support was terrible, and blah, 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 and this thing can go on forever. And you want to have an algorithm that can take any sized input and sometimes also, say in translation, right, translate to variable sized outputs. And we didn't have a good way to do this before. So we had, well, let me get the other point, then I'll say the trade-off. The other thing we want to do is when we look at text of varying scales, we want to capture dependencies that are very local. So hi, I, and I, you know, hi is an address, and I, the relation between them is very, very immediate. And then if we have a document and I talk about myself once in the beginning and once at the end, we want to somehow resolve that that's the same object, right? We want to capture the very long-term dependencies in there. And until deep learning came about, we really didn't have a good way to do both of these, to handle arbitrary input lengths, and particularly long input lengths, and on the other hand, capture the dependencies at kind of an arbitrary length. And that makes a really big difference when you're working with text, because you know, the dependencies and the lengths are arbitrary. They're really up to your user. You have no control over it. All right, so let's see how we do that. This is the technical slide, all right? By the way, let me ask this. How many people, when I say gradient, think of colors? Okay, good. So I won't go too deep into the gradients, but and how many people hate Python? Shame. Okay, so basically the core construct, or the I don't know, the type or whatever you want to call it, in deep learning that allows us to work with text or with sequences in general, this works for prices and temperatures and whatever, is called a recurrent neural network. And basically a recurrent neural network, put simply, it's this box A. This is the code inside of it. And what A is, it's basically a state machine. But instead of having finite states and kind of a trend, how do I transition from this to this? It has these soft states. They're these vectors. They're these bizarre continuous numbers. And what we train the network to do is learn how to move, given an input, how to move from state to state. But the beauty is, if you look at it, like I can input here, and every time I give the box A an input, it does two things. On the one hand, it gives an output, like every good box, right? Boxes should get inputs and give us outputs. But on the other hand, it does this little loop thingy where it updates its internal state. So that means that when I give it, I don't know, I say, hi, I am, then when it considers the output for the second word, it's taking it into account the context that came before it, right? And then as I move down the sentence, every time I give an output, or the box gives an output, it does it with the context of everything that came before it. And that's quite nice because this is exactly what we wanted. We can, using this box, we can put in arbitrary length inputs, right? We can have one example with 2 words and one example with 1,000 words, and both work. And this thing promises us to capture the dependencies, the long-term and the short-term dependencies within the inputs we have. And that gives us what we want. Now, let's skip this. All right, so it gets very complicated very fast. There are all sorts of like wacky architectures. Where's the clock? How much time do I have? I can't see it.
22 minutes.
Okay, so let's talk about this. I have enough time. All right, so let's come back to it. Let's do something simpler first. Okay, so let me show you a really nice example that I like of these things in action. So this is from a guy named Andrej Karpathy. He's today the head of research at Tesla, and at the time he wrote this, he was a PhD student at Stanford. But basically, he took this box, and what he told it to do was he took the Linux source code, all right, all the source code of the Linux kernel, and he fed it in character by character into this box A. And what he asked the network to do was, given a character, or given a sequence of characters, predict the next one, okay? And he just trained it to predict the following character given an input. Great. So once you have that, you can feed it a character. It'll predict the next character. You can take that prediction and feed it back into the network, right? So it'll, you put in A, it'll say B. You take B, you put it back in, and it'll give you C, and you put that back in. And all right, so that's what he did, but he trained it on the Linux kernel. So then, this is code that not a person wrote. This is something that a machine wrote, exactly based on his output. Now, that's cool, right? Because it looks nice, but it has a few really interesting properties. So first of all, it understands comments, right? You open a comment block, you close a comment block. And there's a long range here, right? Because I don't know, there's probably 60 characters between the opening of the comments and the closing of the comments, right? And the machine's capturing, all right now I'm in comment state. I can't continue into code mode before I close my comments. So that's pretty cool. And then it understands function declarations, right? It's static, and I know it's int, and then I need to do it, and then I know, I don't know, what does my function take? I think it's bad practice to say your function takes void, but I don't know, I haven't written C in a while. All right, but here's the thing that, in my opinion, is really the most mind-blowing, all right? Follow the indentations, because look, he opens the function, right? So everything's indented within the first curly brace, and then he opens this if, so everything's indented in there, and then he opens this if, and it remembers if it's one line if, then you don't open curly braces, right? So that's the code standard in Linux. But it does the indentation again, the same for the else. Now, what's kind of amazing here is that this thing's captured dependencies on multiple layers, right? It knows, hey, I'm in 1 layer deep of indentation, 2 layers deep, and it knows to unwind them correctly. And if you think about how we would implement that, so maybe how a parser does that, it follows a stack, right? So all right, stacks aren't that complicated, but the network learned to stack by itself. And that's amazing, because we had to read books in computer science courses to know what a stack is. And this thing just figured it out by itself. And that exactly gives it the ability to track these long-term dependencies in our text, which is, again, very, very cool. Questions? Yes?
It couldn't quite make up its mind as to where to place the opening curly brace.
What?
The same line or after the new line?
No, I think that it's the convention of the Linux source code that function declarations have a different line and if blocks on the same, right? But this is a contested standard.
Right.
So it doesn't follow the one-line if consistently.
Excuse me?
The one-line if, but then below it didn't follow consistently.
No? Why? Where did it cheat?
On before.
Right? You're right. You're absolutely correct. So, right, it loses points for that. Absolutely. Huh?
And go to.
It has a go-to?
Yeah.
Well, I think they have go-tos. So this tells you something, right? They have go-tos in the Linux kernel because it didn't invent C. It only learned from examples. So if the Linux people are writing go-tos, then so are we apparently. Anything else?
There can be one more pattern that a big OS like Linux has multiple contributors, and each developer might have their own coding style. So 7% raise here, 7%
So that could be, but Linux particularly has a very assertive dictator and a very consistent coding style because of that. Right? Great. So let's talk. I want to show you two use cases, and then we have, I guess, time for questions. So this is from a Berlin startup named Raza. And everyone here, I'm sure, has been hearing about chatbots and how awesome they are, right? It's a big buzzword, but honestly, chatbots suck because they don't work. But Raza is building tooling to make it better. And I met with the guys because we like text, so we were chatting. And then they showed me this really cool pilot they did. And I'm like, wow, that's an awesome example. So basically, they hooked up with an insurance company, and this insurance company had like a long tail of customers whose policy was about to expire, but they didn't really have the capacity to call them one by one. And so these Raza guys built a bot that would send an SMS like any normal company would, right? Send an SMS to your clients so they renew. But then they built a bot that can follow the full conversation in SMS to get them to renew their insurance policies. And the really cool thing is they got a 25% renewal rate, which is amazing because you don't have human labor. They paid the Raza guys whatever they paid, but they got a 25% renewal rate on this long tail and this reusable product. And that's fantastic, right? Because it works. That's valuable, right? I don't think I need to upsell it any more than that. All right, and the other thing is, and this is, again, my bread and butter, you want to understand what customers are saying about you, about your product, right? What do they care about? So this is a project I'm doing for a friend, where we want to go through Amazon reviews and understand what are the key features that people are talking about in products to see, what matters. And that's not well defined, right? It's not like you say person, product, right? So you have these attributes like, I don't know, this is about jumper cables. Long cable, okay, so that's an attribute. And then it's built solid, it's nice and tough, it's big, it's hard. So you want to capture these things, and then you move on to a different domain, like books or movies, then you get these other attributes, you need to capture them. And I annotated this by hand, right? Like I had sat down and dragged the mouse, and this is horrible, horrible, horrible work. And you really don't want to do that, and it's expensive. Even if you outsource it, right? If you outsource it cheaply, you get bad results because cheap labor gives cheap outcome. And if you outsource it to experts, it's very, very expensive. So you want to automate this as fast as possible. And this is an area where deep learning, or these techniques are particularly useful because these words, they have meanings based on their context, right? So if we can understand the global dependencies or the area that's surrounding the words of interest, we can make much more clever inferences about them than we could. And then the use cases downstream is that, we can populate our CRM with things that our customers are interested in. We can understand what people are saying about our products and where we should focus our marketing efforts or our product development efforts. So there's a lot of very, very relevant and important information in this text. And the beauty is a lot of companies have it, right? Like companies interact with people via text, and it's there. We save this stuff for years. And now we kind of have the tooling to access that information. So, wrapping up, right, as I said, we as companies, we have text records of our interactions with our customers or of ourselves, whatever, and we can use those records to better serve our clients and ourselves, optimize our business, optimize our products, whatever. And text is really, really hard. Right, we don't really know what we're doing. Norvig said it in '76, and we still haven't gotten much better. But deep learning makes it a little bit easier because we can capture long-range dependencies and because we don't have to do feature engineering anymore. And with that, thank you. It's a bit intense, huh? Questions?
Sentiment analysis progress? Because for instance, on the bird example, it's very clear there has been a massive improvement in the last 3 years, but sentiment analysis seems to be pretty much stuck.
So the state of the art is constantly moving forward. I would say the problem with asking these questions on text as opposed to image. So for image, the answers are very clear, right? In the domain, a bird is a bird is a bird is a bird is a bird, right? And what's going to change is the type of bird and the quality of the image. And I think sentiment is a little bit harder to define. Sometimes I have an example that I took out, unfortunately. So sometimes you'll have a sentence like, there's a classic example on Amazon reviews, right? Where they're reviewing a movie that was a book adaptation. And the reviewer is saying, wow, the book is really, really good. The movie is horrible. What's the sentiment of the review, right? And so you need to drill down into the sentiment of the particular objects he's talking about. And then these things break down a bit. Make sense? On the other hand, though, I will say that in terms of standard tasks that are defined, kind of academics are tracking, then there's new state-of-the-art being hit all the time with this stuff. Sure. More?
So if I can just, there is actually an interesting example, I don't know if you've seen it, where based on text now machine learning algorithms can generate a picture of the bird. So you can just search for this, it's really fun. And so there's a question, so do you primarily work with English language or some other languages as well? And what are the difficulties in other languages that, for example, you don't have in English?
Right, so I work with a mix. So my focus is English because that's, I guess, just the language that business is done in. Then you have, so languages like German. German's amazing, right? Because German breaks all the rules of linguistics, right? Like you have all these phenomena like Trennbauer verbs, right? You have these phenomena in German that they just don't make sense, and all the linguistics books say that's wrong, right? That shouldn't happen in a language. So German's really, and the ability to, German's funny in the sense that you can take a bunch of words and connect them, right? So where does a word start and where does it end? How should you split it? So that's an interesting phenomenon. There are languages that are more extreme in that the atomic unit of writing might be a syllable, or maybe in Chinese we don't even have spaces, right? So then when exactly does a word start and when does it end and how are they interacting? That's an interesting example. In Hebrew, my native language, we don't have vowels. So I saw an interesting example. It was funny, right? But the word for massacre and cook, like the chef, is spelt the same. And there's a news article. Someone said there was something about a massacre in, and someone commented, you know, stupid people. Why are you listening to a chef instead of the police, right? So every language has its own kind of funny phenomena. More? Yeah?
Things like sentiment analysis, how do you defend against bias? You know, so things like sexism and racism that are coming in from the data.
Well, it's a question of do you need to, right? So if you're using internal tools, bias is a fact of the data, and you know that who cares, right? It depends on the task. If you're Facebook and you're doing something consumer facing and it's going to be a PR fiasco, then that's a big problem. But
on the internal data, you know, supposing you're using it to drive a recruitment system,
right?
You may have a cultural bias towards white males in your organization.
Yes, that's
your data's a problem.
Yeah. That's I think that's generally true, right? You're only going to get results that reflect your data. If the process that generated your data is biased in some way, so biased kind of in the negative connotation of, I don't know, we like white males, or biased just I don't know, there's some statistical bias there, then your system's going to reflect it. And then the first thing you need to do in order to prevent that is know about it, right? And you're not going to be able to defend against that if you're not aware of the problem. And once you are, then you can usually rebalance your data in some form to get kind of the distribution you're looking for. So I think there was an automated system for granting parole in the States that was very, very biased. And eventually they went into correcting it exactly for these reasons, right? Anything else? Yeah?
So what's the story behind your T-shirt? Because you spoke so much about deep learning, but if I get that right, support vector machines is between statistics and between deep learning. And
right. So
seem to be fond of the middle.
Right. So before deep learning became big, support vector machines were like the
state of the art.
Yeah. So what's beautiful about what's really nice about them, so the classic machine learning now are like logistic regressions. They're linear classifiers, so that means like the examples that you showed, you have your data points and you can only draw a straight line. You're always looking for like clever ways to draw a straight line. What support vector machines can do is they have this clever trick where you can kind of make believe that your data is in some different geometry, right? But it's all make believe. It doesn't really happen. Like you don't have to compute it. But then instead of having to separate it with a straight line, you can separate it with this crazy zigzag, right? And the algorithm will find it. And that's why they were the state of the art. And my girlfriend bought me this shirt because, you know, she thought, you're a geek, you like this stuff. So here you go. And I like it. And it's always nice to wear it when I talk about neural networks. Anything else?
Is there an example? You spoke about algorithms to do text automatically, right? Is there any example by a book, for instance, written by a...
Yeah,
Do you see this in the future? Like,
so there's a really cool site online called, I forgot its name, but so this guy did an experiment. He's like, very much like the example I showed with C code. And he was like, can I learn to make clickbait, right? He's like, basically, look, I'll train on like BuzzFeed titles and articles. I'll make a bunch of clickbait. I'll get a bunch of Google traffic. I'll put ads there and I'll make a bunch of money, you know, generating content automatically, which is a smart idea. And he does that. So the titles he gets are really good. Like they're funny, they're witty, they make sense. But kind of on a longer term, like a paragraph, we still are terrible at. Like it doesn't make sense. The grammar is correct. Like you can read it and say, this sentence is correctly phrased, but it doesn't make any logical sense, and there's definitely no like proper sense between two sentences or definitely two paragraphs. Right? We're very, very far from that. Okay, thank you.
Thank you very much, Tom.
Pleasure.
Guys, we're gonna have a short